This video is about limits at infinity, and we will look at limits at infinity of polynomial functions. To talk about limits at infinity, we want to talk about what happens to the function values if the independent variable becomes arbitrarily large in magnitude. That means very large positive numbers or very large negative numbers. So we say that a limit at infinity is L if the function becomes arbitrarily close to some finite number L for all sufficiently large positive values. Then we say the limit as x goes to positive infinity of the function is L. And then if we want to go to negative infinity, then we say that the limit of f of x as x approaches negative infinity of the function approaches some finite number m. If that's true, when the limit exists, either L or m is a horizontal asymptote. So an example might be something that looked like this, where as x becomes arbitrarily large, your function f of x gets closer and closer and closer to 0, and that would mean that the line y equals 0 is a horizontal asymptote. So let's take a look. We do need to know a note, something like we had in a previous video, that says if the numerator of a function remains relatively constant and the denominator grows arbitrarily large in magnitude, then the function, or the fraction becomes arbitrarily small. So you might be thinking of something like 3 over 100, 3 1,000ths, 3 1,000,000ths. As that denominator stays, or the numerator stays the same and the denominator gets larger and larger, the fraction actually becomes smaller and smaller. So let's take a look at this first example. We have the limit as x approaches infinity of 5 plus 3 over x plus 4 over x squared. Well, as these two denominators grow without bound, the limit of these two pieces is going to go to 0, and we just have the limit as x approaches infinity of 5, which is 5. So let's take a look at this next example. This one's not so easy because certainly we could take the limit as x approaches infinity of 3 and then add it to the limit as x approaches infinity of sine x over x. But remember, we said that the numerator had to remain relatively constant. And in this case, as x gets larger and larger, we know sine oscillates between -1 and 1. So even though our x value is getting arbitrarily large, we can't say that the fraction itself goes to 0 because our numerator is not staying constant. So we have to use the squeeze theorem here, and we can start with the fact that sine of x is strictly between 1 and -1. And if we then divide each piece by x and take the limit, we get the limit of -1 over x as x approaches infinity is 0. And the limit of 1 over x as x approaches infinity is also 0. So we can say that the limit of sine x over x as x approaches infinity is 0. So over here now we have the limit as x approaches infinity of 3 is 3, and the limit as x approaches infinity of sine x over x is 0, and we just get 3. Okay, what if we have a function that as x grows arbitrarily large or arbitrarily small, the functions also get arbitrarily large or arbitrarily small? Well, we call that an infinite limit at infinity, and it looks just like this. The limit as x approaches infinity of a function equals infinity. And of course, we could change the infinity to a minus infinity. In all of those are defined analogously. Okay, let's take a look at an example, a polynomial function, in this case just a simple x cubed. So you should know that the graph of an x cubed function looks something like this. And we can see from the graph that as x gets arbitrarily large, the function value grows without bound. And so our limit as x goes to infinity is positive infinity. Similarly, if we let x get arbitrarily small, our function values are getting also arbitrarily small, or actually large, negative numbers, and that also, well, in this case, will give us negative infinity. And this is similar for all polynomial functions, because when we have a polynomial function, 5x to the 7th plus 6x to the 4th, 3x squared plus 8, this term right here is what we call a dominating term. It dominates everything else that's going on. And so if you think about plugging a very positive, a very large positive x value, this is going to grow without bound. And if you plugged in a negative large number but raised it to the 7, you would get a negative very large number. So we can just determine what's going to happen just using our leading term. So that's what this theorem here says. It says that if we have a positive integer n and a polynomial p, and this is just that polynomial in general form, where the leading coefficient is not 0, then the limit as positive or negative infinity, as we go to either of those, is going to be infinity when the n or the exponent there is even, and it's going to be positive infinity or negative infinity when n is odd. So let me see if I can explain that. If you take the limit of 5x to the 4th plus 3x as x grows arbitrarily large, since I'm raising it to an even power, I know I'm going to get positive infinity. Even if I was going to negative infinity, again, because the power is even, we're multiplying an even number of times, we'll get positive infinity. However, if we have an odd function, 7x cubed, for example, a positive cubed is going to give us positive infinity, but a negative value cubed is going to give us negative infinity. So we really just need to look at that leading term. We already talked about this rule here that says if the denominator of a fraction gets arbitrarily large or arbitrarily small positive numbers, then our limit is going to be 0. And for a polynomial, we just need to look at the leading coefficient a sub n and the degree of the polynomial. So let's take a look at a couple of examples. In this case, we have the limit as x goes to infinity of 5x squared minus 3x plus 2. So this term here is going to tell me what's going on. If I raise a positive large number to the second power, it's just going to get larger, and it's still going to be positive, so we get infinity. For this next one, again, this leading term is going to tell us what's going on. So a negative value squared would give us a positive value, and it would be very, very large. But we also have this negative sign in front, so the limit here is going to be negative infinity. So see if you can do the next two examples. You might want to pause your video, and I will write down the answers. Okay. When we want to look at these in general, we've already seen all of these rules. So let me write a little table here off to the side. If we have a polynomial, we talked about the end behavior by looking at whether the degree was even or odd and whether the lead coefficient was positive or negative. So if we had an even degree and it was positive, we knew it was going to go up on the ends, and if it was negative, it was going to go down on the ends. Similar to, say, an x squared. Now an odd, if it was a positive degree or positive lead coefficient, it's going to go up in the first quadrant and down in the third, versus an odd with a negative coefficient will go up in the second quadrant and down in the fourth. So you probably learned that in a previous algebra course, and that can also help us when we're finding these limits. I am going to leave the end behavior of rational functions for the next video. See you next time.